today we are going to figure out the electric field located along the axis of a uniformly charged ring of charge, positive. So we have a ring that looks remarkably like my roll of tape. It will be oriented like this. I'm going to draw it as such. That's quite how I want to do it. So basically what I'm drawing is the cross-section of the ring. So the ring goes, nah, that's not good. I don't like that. We'll do it this way. I'll try to draw this way.
Not like I'm writing a pen.
Bless you.
Bless you. Don't have to look.
I don't know. I'm trying. Here we go. It's a ring that looks like this. Nah, that's worse. I can go back to what I had before. Okay, so here we go. It looks like this, and this is the cross-section of the ring. So it's a uniformly charged, uniformly positively charged ring. And that positive charge is positive big Q. And what we're going to do is we're going to figure out the electric field at a point P. And at this point, which I've labeled P. This point P is located a distance x from it along the axis, and the ring has a radius of lowercase a. For those who are curious of what this little piece is right here, you're looking at a cross-section of the ring. So if I were to take the ring and were to cut it along here, you would see this portion, and then this portion you would see in the background. But you see the interior of the ring right here and here. That's what that symbol means. All right. So our known values are A, X, and positive big Q. Our goal is to figure out the electric field. Class, is this a point particle?
No.
All right, we'll try that again. Is this a point particle? No. Okay, good. So what we're figuring out is the electric field of an object that has shape, a uniform charge distribution, if you will. I do want to pause for a moment and point out that, no, we'll do that in a minute. It'll make more sense in a minute. Okay, so the electric field, what's the equation we're going to use to figure out the electric field of a uniform charge distribution, not a point particle? Tim?
Force electric over Q.
It is not going to be the electric force over Q. That would be if we had the electric force, we could then solve for that. That is a true equation. That's not what we're going to use here. Meg?
E equals KQ over R squared.
E equals KQ over R squared is another equation for electric field. It is not the one we're going to use here. This is the equation for the electric field around what, Sarah Jane Jones?
A point charge?
A point charge. Class, is this a point charge? No. Okay, slowly but surely we will get there. We are going to use what equation? Emily?
K times the integral of dq over R squared.
So we're using the equation for the electric field equals K times the integral of dq over R squared unit vector R. Note, this is essentially taking this equation and just breaking our little ring here into little charges dq. Eric?
What's the difference between the capital Q and the small Q?
I'm going to use that today, but generally the capital Q is the charge on an object that has shape. The little q is a charge for, say, a point particle, and dq would be a small portion of big Q. All right, so if you look, we're going to break our ring into a whole bunch of little charges dq. So this piece, if we look at it, here, I'll try to draw it again just for fun. If we take our ring, we're going to break it into little dq's. So this is dq. So we have a dq, which is located right there. And we're going to figure out the electric field due to all of, the sum of all of these dq's. Let's start out with the first one. Please, class, point in the direction of the electric field at point P caused to dq, which is at the very top of this ring. Please point. Okay. That electric field due to dq is going to be in this direction. And we will call that dE. The electric field is defined by what sort of test charge? Mohit.
I have no idea.
That's sad. Sorry, it's here.
A small positive.
A small positive test charge. So when we're talking about what's the direction of the electric field right there, it's like taking a small positive test charge and placing it right there and saying, what's the direction of the force acting on that? So it would be, in this particular case, in that direction, and that would be dE. Now, we could go through and talk about every single one of the dq's, but I want to point out one specific one, which is the dq, the electric field caused by dq on the bottom here. Please point in the direction due to that one. Okay. That one is going to be pointed up in this direction. So if you'll notice, the dE's in the y direction from both of those dq's cancel one another out. And for every single one of these dq's, there is one 180 degrees from the other one where all the electric fields in the y direction are going to cancel out. So please point in the direction of the net electric field at point P. Right. Notice all of the dE's in the y direction cancel due to symmetry. So when we're figuring out the electric field total, it's going to be equal to dE in the x direction. All right, so we need to figure out dE in the x direction. We have this, which is r, this, which is theta. Notice r and theta are not known values, but we can derive what they are from the known values. When we look at this, we get dE is equal to k times dq over r squared unit vector r. Okay. What is r squared equal to? R squared, Nitish, is equal to?
A squared plus x squared.
Okay, so dE then is equal to k times dq divided by a squared plus x squared times unit vector r. Okay, what about dE in the x direction? dE in the x direction is equal to what? Zach?
dE cosine theta.
dE cosine theta. Considering the fact that the cosine of theta, which is this angle right here, is equal to adjacent over hypotenuse, we can see that dE in the x direction is equal to dE times the cosine of theta. So when we take the integral of both sides of this, we get that the electric field total is equal to, actually I don't quite want to do it that way. Let me bring it up here. So what we get is, coming back to take the integral, we get the electric field total is equal to, bless you, dE, which we know is equal to, no, I want to do it in two steps. So dE is equal to taking dE, which is equal to k times dq over a squared plus x squared times unit vector r times the cosine of theta. Let's look at this step by step. We know unit vector r. We've already figured out direction. So we know unit vector r is actually just in the I direction. We've already figured that piece out. we've now got k dq over x squared plus x squared, a squared plus x squared. We need to take the integral of both sides. When we do that, we get the electric field total is equal to the integral of k times unit vector I, actually let's do that at the end, times the cosine of theta times unit vector I dq divided by a squared plus x squared. We need to look at cosine theta. Cosine of theta is going to be equal to, by definition, Emily,
Adjacent over hypotenuse.
adjacent over hypotenuse. Looking at our triangle here, the adjacent is x, the hypotenuse is r. What is r? Mike? R, in terms of things that we know. Close. Jenkins?
Square root.
Square root of, because a squared plus b squared equals c squared, so it's going to be the square root of a squared plus x squared. So we can substitute in x divided by the square root of a squared plus x squared into this equation. We get that the electric field total then is going to be equal to k divided by a squared plus x squared multiplied by x divided by the square root of a squared plus x squared I dq. Okay, let's get things together a little bit so we can work with it. We have the integral of k times x divided by the quantity a squared plus x squared times the square root of a squared plus x squared. We've seen this before. We saw it last time. Travis is?
A squared plus x squared 3/2.
To the 3/2 power. We still have the unit vector I and dq. Okay. What can we take out from underneath the integral? What are constants? Look.
X or K.
Okay. So what you need to do is you need to ask yourself, does, for example, x depend on which dq you choose? No. Notice x is a constant variable for every dq. Okay. A as well is independent of dq. So a squared plus x squared to the 3/2 power. What's the integral of dq, class? Q. So it ends up being equal to k times big Q times x all over, actually, the x there, times x all divided by a squared plus x squared to the 3/2 power in the I direction. That is the total electric field. All right. What if, for example,
At point P.
say again?
At point P.
I'm sorry, yes, this is specifically at the point P. Oh, that reminds me. What I want to point out is this. We could figure out the electric field located at a point, we'll call it point Z, over here, which is located a distance, I don't know, blank from blank over here. Notice, the physics would be exactly the same, right? We'd be doing all the same physics. But the math would be extremely difficult to try to figure out the electric field at this point, because the electric fields in the y direction are not going to cancel due to symmetry. Is this class a math class?
No.
No, it's not really a math class. Yes, it uses a lot of math, but math is not a primary function of this class. So we are only going to figure out electric fields at specific points. For example, here, we're only going to figure it out along the axis here, not over here, because it doesn't do us a whole lot of good, because this isn't technically a math class. Okay. What happens if x is much, much greater than a? What happens then to x squared plus a squared? X squared plus a squared is approximately equal to what, Hillary? x squared. If that is true, the electric field total then is going to be equal to k times q times x divided by x squared to the 3/2 power in the I direction. What's x squared to the 3/2 power, Eugen? What's x squared to the 3/2 power, please? X to the third. In other words, kq over x squared in the I direction. Please explain why that makes sense, Dorfstedt.
What?
Why does this answer make sense if x is much, much greater than a? It's okay, she's not seeing it. Who can help? Why does that answer make sense? Paderella.
Because that's like pretty much like a point charge, it's just like 1 point.
The farther you get from this uniformly charged, positively charged ring, the more it acts like a point charge. If you get far enough away, this is kq over r squared. Right? It acts like a point charge. Okay, what if a is much, much greater than x? Well then, x squared plus a squared is approximately equal to a squared. Well then, the electric field total is going to be equal to kq times x divided by a squared to the 3/2 power in the I direction, which is going to be equal to k times q times x over a cubed in the I direction. Okay. Let's keep a little space for this. Well, let's say then, let's put a negatively charged particle along the axis of the ring right there. If we were to do so, there would be a force classically pointed in the direction to the left, because if we use a negatively charged particle, it's going to go in the opposite direction of the electric field. So there would be an electric force acting this way because it's a negative charge. When we do so, if we sum the forces in the x direction, we get the negative electric force is equal to mass times the acceleration in the x direction. Well, we know that the electric force is equal to q times the electric field, which is equal to mass times the acceleration in the x direction. We can substitute in the electric field here, so we get negative. Now, this is where we're highlighting the difference between little q and big Q. So this is negative little q times k times big Q times x divided by a cubed is equal to mass times the acceleration in the x direction. So to be clear, this little q it describes the point charge, which is located right there. This big Q describes the total charge on the non-point charge or the uniformly charged ring. Anybody see it? Yes?
It's pretty close to KQ1Q.
No, not where I'm going. All right, I'll rearrange it. Let's see if it helps. Let's see. We'll go acceleration in the x direction then is equal to negative times q times k times big Q divided by a cubed times x divided by the mass. All right, I'll do one more step. We know that the acceleration in the x direction is the second derivative of position as a function of time, which is equal to negative q times k times big Q divided by mass times a cubed, this whole quantity, times x. Little q, k, big Q, m, and a cubed are all constants. True?
Yeah. Simple harmonic motion.
I'm sorry, who's got it? It's simple harmonic motion. The second derivative of position as a function of time is equal to negative omega squared times x. Omega is equal to the square root of q times k times big Q divided by ma cubed. In other words, this is equal to the change in theta over change in time, which is equal to 2 pi divided by the period. Therefore, the period is equal to 2 pi times the square root of ma cubed divided by q k big Q. If you were to take a point charge and place it along the a negatively charged point charge along the axis of a positively charged, uniformly positively charged ring, it will go back and forth in simple harmonic motion, and we just figured out the period of that motion. We could also, if you want, go through and figure out the position as a function of time, the velocity as a function of time, the acceleration as a function of time. Think of all the different things we could do right there. Oh, isn't that fun? All right, good. I'm glad you enjoyed it.